Hello guys, this is the second video for this week. So this is about how to control pumps. Okay, so pump control. So before we go into control, I would like to define two things: efficiency of the control and specific energy consumption. So efficiency is useful divided by input power, as always. Now, in the case of the control, this also holds, but it needs a little bit of explanation. So imagine that you have a desired flow rate on a pipeline system. Okay, then useful power is the power corresponding to this desired flow rate times the pressure difference at this flow rate on the pipeline system, which is rho g h pipeline at this flow rate. So what would be the head and the flow rate and the power that would be needed to push this amount of flow rate into the pipeline system? Okay, whereas the input power is simply the input power of the pump. Okay, you will see in a minute that these two numbers can be pretty much different, but for the time being this is enough. So useful is the desired flow rate times the pressure difference of the pipeline system at this desired flow rate, while the input power is the pump input power. Now there is another quantity called specific energy consumption. This is the pump input power divided by the flow rate. Now, the desired flow rate. Now, flow rate is volume divided by time. So if you multiply power by time, that's going to be energy or work divided by volume. This is joule per cubic meter. Okay, or kilowatt hour, or equivalently, clearly after some kind of unit conversion, kilowatt hours divided by cubic meter. So this simply means that specific energy consumption is the power consumption or energy consumption that was needed to convey 1 cubic meter of fluid into the system. So this simply means that with a specific control, I need this amount of electric power to push 1 cubic meter of liquid into the system. So both of them are important. Think, for example, in terms of a water distribution company. The sold water, the amount of water that the water distribution company sold is its incoming money, while the electric bill is the outgoing money. So this is a economical quantity. So this is a amount of money paid for the electricity provider. So this is a outgoing money, whereas this is income, the amount of fluid water sold to the customers. So clearly you want to have this number as small as possible. Another important bit is the so-called ISO efficiency lines. So take, for instance, this pipeline pump curve. So you have here pump curves at different revolution numbers: the blue, the yellow, the purple, and the red. And you have the efficiency curves. Now what you do is that you say that this is an efficiency, let's say 80%, and then this efficiency belongs to this point. And the same efficiency happens at this point if the revolution number is the blue one. Now at another revolution number, the very same efficiency here corresponds to this line and this line here, this point, sorry. Then for this, the other two revolution number, let's say 80% is this and this. And then you simply connect these dots, and then you'll get the line, the curve corresponding to constant 80% efficiency. And you do this for the rest of the efficiency values. And then you get lines which, and in between these regions, the minimum efficiency is 80%. So let's say that if this line here corresponds to 85% of efficiency, then all the operating points within this region have at least 85% of efficiency. Okay, so this is important because this shows that which are the head and flow rate regions in which your pump works with good efficiency. For example, this is a case of a true head curve. I'm sorry about the mistake, but you can clearly see that these are the ISO efficiency lines here. Okay. Okay, now about controlling the the pump. Imagine the following case. You have the red pump and you have the blue pipeline curve. Okay? If you simply connect them, then this will be your operating point and this will be your flow rate. Now let's say that you are not happy with this flow rate because you want to have a smaller flow rate, which is this Q desired. So our task is to set this desired flow rate, and what we will do is that we add a valve at the pressure side of the pump. Now what happens now? We have three elements: a pump, a valve, and a pipeline connected in series. So as I explained in the last lecture, if they are connected in series, then the flow rate is the same. So all three elements experience the same desired flow rate, which means that this is the pump operating point. Okay? So if the pump's flow rate is Q desired, then this is the pump operating point, and this is the pipeline operating point. What happens is that I would need this pressure difference for the pipeline, but the pump makes too much pressure. So what I do is I add a throttle valve, and with the loss of the throttle valve, I get rid of the extra amount of pressure. So clearly, this is a very poor choice in terms of energy, because what I do is that I increase the pressure of the fluid in an unnecessary extent, and just after the valve I get rid of it. Okay, but this is a very simple way of controlling. And then please have a look at the lecture notes. The efficiency of the control and the specific energy consumption is nicely explained, but it's fairly simple. The useful power is, as I said, the desired flow rate and the head of the pipeline. So this will be here the useful power. Okay? So I will write here for you Q desired rho G H pipeline at the desired flow rate. But this is essentially, so this is this point here. Now the input power is the pump's input power. The input power is the hydraulic power divided by the efficiency of the pump. The pump's operating point is this point here, so the efficiency evaluated at the desired flow rate, and the hydraulic power of the pump is Q desired, again because this is the flow rate of the pump, rho G H. So this is pipe here, this is pump. I will write it here. Pump at the desired flow rate. Okay, so that's essentially this area here. This is the hydraulic power divided by the efficiency of the pump. And that's going to be the input electric power. Okay, let's have a look how the same thing happens if you have a parallel connection. Now the parallel connection, so the issue is the same again. You have the red pump, you have the blue pipeline, this is your operating point, and then you want to set this desired flow rate. So now you add your valve in parallel. That's something we call a bypass valve. So now all three elements are connected in parallel. So the head is the same because the pressure difference is the same. Ambient pressure here, here, and here. And here the pressure is common, so the pressure difference is the same. And the pressure difference is again the head of the pipeline evaluated at the desired operating point. So if this is the head, then this will be the flow rate of the pump. Okay, so this is the flow rate of the pump. This is the flow rate of the flow rate need of the pipe. So previously my problem was that the flow rates were okay, but the pressure was too large. Now the pressure is okay, the pressure is what I need, but the flow rate is too large. So what we do, we get rid of the unnecessary amount of flow rate through the valve. Okay, fairly simple. Again, when computing the useful power, this is always the system useful power, and now the pump operating point is this. Finally, let's speak about the revolution number change. So very often we control the flow rate of the pump by changing the revolution number. So intuitively, if you decrease the revolution number, then the flow rate decreases. If you increase the revolution number, the flow rate will increase. Of course, we have to use the affinity laws, which I have already explained. But there's a new bit here. If you combine these two affinity laws, then you get this equation. So H2 is something times Q2 squared, where this something, this constant, is H1 over Q1 squared. So this is a very important equation. This tells us that whenever you're messing around with the revolution number, let's say you start with the operating point Q1, H1. So whenever you're changing the revolution number, this operating point moves along a parabola which starts from the origin and is quadratic and passes through the H1, Q1 point. Okay, so let's see again our problem. Again, pump, pipeline, this would be your operating point without control, but you want to set this operating point here. This is your desired flow rate. Okay, now, very often my students are happy that they have two operating points, one here and one here. Okay, and they start using the affinity laws between these 2 points. Okay, but this is incorrect. This is incorrect because, as I said, if you pick an operating point and you start varying the revolution number, the operating point will move along a central parabola. So for instance, this operating point on the pump performance curve, if you start decreasing the revolution number, will move like this. Okay, and this will not go through the desired point at the pipeline. So what you need to do is the following. Again, you have the original pipeline, the pump curve, you have the pipeline curve, and you know that you want to have this flow rate, and you are searching for that revolution number at which the pump characteristic curve passes through the desired flow rate here. So what you do is that based on this point, here you find A, that is your affine parabola, your central parabola, that's the red curve here, and find this intersection. And then you can use the affinity laws from this point to this point to find the unknown revolution number. Okay, so you know You know H2, it can't be C, that was H2. So you know H2, you know H1, and you know the second revolution number. It doesn't matter which one is 2 and which one is 1, so you can easily work out N1 or the other way around. And if you happen to use the flow rate equation, so Q2 over Q1 is N1 over N2, then you'll get the very same revolution number. Okay, so this is important, think it through, and there is also a verbed example in the problems section. Okay, so again, please have a look at section 5 in the updated lecture notes. Okay, have a nice week. I wish you a happy Easter. Take care. And as I told you, I will not upload a video next week in fluid machinery because we've sort of finished up the pumps and pipeline systems part, and I want you to have a look at all these video lectures, have a look at the lecture notes, practice yourself, and especially with this series and parallel connection part, it's very important that you not only listen to these videos, but you also practice for yourself, make yourself sketch, solve problems, etc. Okay, see you.